So, I am Dr. B.M. Kulkarni. I have joined as R&D head of this Go Green Fuels. So, basically, they are in Go Green development of green fuels. So, they approached me, why can't we join us group? So, I am there with them since last almost 2 years. But my association with them, it dates back to about 8 to 10 years. He is from Harihar. Harihar is about 8 kilometers from Davangere. So he used to come to my laboratory, see whatever things or all those things work was going on. Okay, next project. Many of you people don't know how diesel engine was developed. In fact, the fuel used for diesel engine was peanut oil, not diesel. Rodolph Diesel developed the diesel engine in the year 1901, demonstrated in the execution, and the oil used for running the diesel engine was not petroleum. At that time, petrol was not known. So he reused peanut oil for running the engine. At that time, he made a statement: diesel engines have to be fed with vegetable oil, as it supports considerably development of agriculture and countries which use it. At that time, during 19th century, because they wanted to add value for the vegetable oil. Large amount of vegetable oils were there, which were used for only small amount of edible purpose, rest was not known. So he made a statement: diesel engines have to be fed because it supports agriculture and countries which use it at that time. But now the trend has reversed. Global warming, food security, water shortage, all these things have overcome. So United Nations during 21st century, this is a statement made by them about 5 or 6 years back. There are links between biofuels and food security. In fact, 2005, you see Times Magazine, at that time, who was president? 2005, he was begging for corn from Africa to run his cars, ethanol. So that created a different, altogether different picture for the biofuels. We should not use food items for any fuel. So they told there are links between biofuels and food security, because at that time most of the biofuels were produced from food sources, like ethanol from sugarcane at that time, biodiesel from and I think corn was using for it, and biodiesel from vegetable oil. Both are the oil for food sources. So they made a statement: diversion of food crops to fuel is a crime against humanity. Nothing else. So at any cost, there should not be a conflict between food and fuel. That's the policy of the United Nations, and today it is made mandatory also. Okay, next slide, please. Yes, what was the need for going for biodiesel? Increased pace of global warming, public perception of dangers of global warming, proven roles of diesel fuels in global warming affairs have necessitated countries across the world to look for an alternative fuel to petroleum fuels. Okay, biodiesel and bioethanol are projected as viable alternative to diesel and gasoline fuels. Even today also, they are projected gasoline. Biodiesel, though attractive, is not viable at present due to its high cost. When compared to diesel fuel, high cost is mainly due to usage of refined vegetable oils during manufacturing operation. Again, I told him at that time it was mainly reason. To reduce biodiesel high cost and make it competitive to diesel, alternative feedstocks have to be identified and proper processes have to be developed. Then only it can be made competitive to diesel fuel. Next slide, please. Yes, what is biodiesel? First, I told you already. To your surprise, also, I'm telling this is a statement made by me only. Biodiesel is a biofuel prepared from biological source like vegetable oils, animal fats, whose properties are closer to diesel fuel, which can be used at existing diesel engines, so that engine modification problem will not arise. And what it consists of? In engineering language, you say Technically, biodiesel is a mixture of fatty acid methyl ester compounds. It is basically a mixture of FAME, we call it as FAME, fatty acid methyl ester compounds. What they contain? FAME compounds are aliphatic chain hydrocarbon compounds containing carbon and hydrogen long chain. They contain. This is all statement. I made a statement based upon the spectral observation, nothing else. A methyl group at one end of the chain and an ester group at the other end of the chain. A long chain is there, one end methyl group is there, another end ester group is there. Number of saturated and unsaturated hydrocarbon bonds are spread across the chain. The carbon chain does not contain any aromatic. That is very important step. No aromatic compounds are present in biodiesel and even branching. But in diesel, they are predominant. Branch chain compounds are there, aromatic compounds are there. That is the main difference between the diesel and biodiesel. A typical structure of FAME compounds is shown as follows. A carbon chain is there, one end methyl group, another end ester group. Next, please. Properties of biodiesel. Can we vary? Yes, definitely one can vary biodiesel. Yes. Properties of biodiesel are decided by number of carbon atoms in the chain. Long chain, I told you. How many carbon atoms are there? 10 to 12, 12 to 15. Depending upon the carbon chain, properties can be changed. And this carbon chain is not same for all oils. It changes from oil to oil, and even it changes from region to region. Environmental factors come into picture. So, number of saturated and unsaturated groups are present in the chain, not one or two, number. In some oil, they are random, but in most of the oil, they are precise. Alternatively, all these groups are going to be there. Properties like viscosity, spectral investigations like IR, UV, NMR, carbon, NMR, protons have confirmed the above statement. All have confirmed the above statement. Viscosity, flash and fire point, calorific value, CTN number, etc. are all influenced by these. All, even a slight change in there, we can change the compound. So, we can tailor the fuel according to our requirement just by changing this number of groups. Carbon chain size and number of saturated, unsaturated compounds vary with the source. I told you same statement. Okay. This has resulted each country to specify their own biodiesel standard to protect the commercial crops of their country. In fact, in India we say, what is the reason, sir? Jatruba fuel, India. To protect, because Jatruba fuel is grown in our country by the farmers. If you go to America, soybean. Change country to country to protect their farmers' interest, they have made that standards. Nothing else. So, International Standard Organization has also specified their own standards for trades. If you want from one country to another country, we must mention this fuel. Okay. Why acid oil? Why acid oil comes question? Many people have asked me, why only acid oil? Why not use raw oil? Why not use raw oil? Raw oil, its problems are so many. It contains acids plus oils also. The conditions required for reactions are different. So, any feedstock chosen to be attractive should be the conditions ready available in large quantities at few centers. I can't go on collecting half a liter from here, half a liter from. It should be readily available in bulk quantities. That was condition. Should be reasonably low price. Reasonably priced, not cheap. This is competitive. It should be reasonably priced. Should be available locally, so that taxation problem, import exports can be minimized or avoided. And the process should be environmental friendly, because every process there is a effluent. So now more concern is on effluents. Disposal of effluents is going to be there. So that is the first question we should know. As an engineer, now I say the products what you discharge should be eco-friendly, so that they do not cause any harm on the environment or on the people. That's first concern. India produces about 4 to 4.2 million tons of acid oil at 1,060 vegetable plants at present in the country. The cost of acid oil is about 45 to 50,000 rupees per ton. It changes from source to source, location to location. Around 40 to 43,000 rupees you get today also. Then ED3R esterification process developed is easy. This what process what I have developed is easy and can readily be scaled up to commercial scale operation, because most of the process involves several steps are there, but all steps are not new steps, already proven and established in commercial operation. The process does not produce any large scale toxic product. Only product is water. No glycerin also. Only product is water, which is environmentally friendly also. Pollutants as recycling and reuse of feedstock materials is done. Though we use methanol, not even a drop of methanol is left. We are recycling it and reusing it. That's the beauty of the process. Next, what is acid oil? Acid oil are a vegetable oil refinery byproducts produced during refining operations of vegetable refineries, which are rich in free fatty acid. Acid oil predominantly contains saturated, monosaturated, polyunsaturated fatty acids. The color of the product is very dark brown and it has an oily texture, liquid with pungent smell. Because of the tocopherols, coloring compounds are there, so it has got a pungent smell. Palmitic acid, what are there? Palmitic acid is there, stearic acid is there, oleic acid is there, and linolenic acids. These are the four major free fatty acids present in most of the vegetable oil, but relative amounts they change. Since relative amounts change, properties of fuel also change with the feedstock what we take it. How much availability is there in acid oil is there? I told you. At present there are 1,060. This is a source taken just last week from the internet. Ready? You can go and check up. At present there is about 1,060 vegetable oil refineries operates in India. They process about 25 million tons of vegetable oil. Even today we are importing, largest importer of vegetable oil in the world. So most of the foreign exchange goes for importing petroleum. Next is vegetable oil, and generate about 4 to 4.2 million tons of acid oil at refinery sites. So around 42 to 45 rupees per kg acid oil you can get at refinery sites, not in liters or kgs, tons and tons of material available. Next slide, please. Yes, this is the typical composition of acid oil what I have taken. Free fatty acids 88.1, mineral acids, because acids they use it for washing in refineries and all, so around 1.1. Moisture content is 2.2, unsupportable matter is 8.6, and surprisingly no vegetable oil. No vegetable, because they separate it. They separate from the oil. Next, yes, chemistry of biodiesel. How I do it? Biodiesel from acid oil is produced from a newly developed ED3R esterification process according to the reaction. That is, this is the free fatty acid, methanol, acid catalyst, and heat. Heat is added. You get ester compound plus water. This is a reaction. No glycerol is produced because no triglycerol is there. No glycerol is produced in the product. Okay. Observation of the reaction features. The reaction is reversible. Acid catalyzed. That's why I put both arrows on both sides. Acid catalyzed, reversible. Reaction is endothermic. Heat has to be supplied. Large excess of alcohol increases the yield. If you increase the methanol, it drives towards this reaction. If you decrease it, again it goes back to the reverse reaction. So methanol also has to be, large excess of alcohol, methanol is required for this. But since methanol is costly, if you don't recover it, all your profits will go down to zero. So you should have a recovery plant also, so that methanol, excess methanol, though I am going to use it, I recover it, then reuse in the process. That should be the problem. Okay. Increase of temperature increase the reaction rate. Heat addition is necessary for the reaction. No need of refined vegetable oils. Don't take at all because they are not involved in the reaction. Then fatty acid mixture can be employed for biodiesel production. Next slide. Yes. What are the variables affect the process? I have summarized it. Acid to alcohol ratio we call it as R. Increase of R increases the rate of reaction. Temperature, increase of temperature increases the rates of reaction. Heat addition increases the rates of reaction. Moisture content is, because moisture is towards right reaction, right side. So if any moisture is there, it opposes the forward reaction. So moisture content reduces the esterification process. Water which is produced, so since it is reducing, water it is produced during the reaction has to be removed from the product biodiesel acceptable quality. So if at all you want to make any biodiesel produce, so water immediately produced has to be removed from the mixture. Then only you get biodiesel, otherwise no biodiesel. Strong mineral acids like sulfuric acid, HCl are used in the process. Continuous addition of alcohol during the course of reaction is required because you have to maintain large excess of alcohol. Alcohol is consumed in the reaction. So you have to continuously go on feeding alcohol during the course of the reaction. These are the conditions which are required. Now, my entire process of development, whatever next stage operation, are based on two particular papers. So this is old paper about 1940s, remember. Two people, what they said is, if at all you want to do any esterification, at that time they didn't have any idea about biodiesel and all those things. So what this word, free fatty acids can be reacted. This is the paper which I got it. That means, oh, there is a process which can be used for converting fatty acid into film compound. Then what they told, okay, see, this is the catalyst they told. Then this is acid catalyst, this is acid catalyst, this is alkaline catalyst. So both can be used, they told. But here, in my case, it contains fatty acid. If I use alkaline catalyst, it will form a soap. Fatty acid plus alkali will give me soap. So I can't go for this. So I have to go only for acid catalyst, nothing else. Then they form a soap, I can't use it. But if you use vegetable oil, they use alkali as a catalyst. They don't use acid as a catalyst, they use alkali as a catalyst. Because there is no acid there, refined oil, only oil is there, then they use, because, next slide please. Then, most important one is moisture. Even a 2% moisture, you can just see, is able to reduce by half, almost half. Even moisture content, as moisture content increases by 4 to 5%, reaction completely stops. So your primary aim should be how you remove water produced in the reaction. If you don't remove it, you cannot get any biodiesel. These are two conclusions which I got from these two papers, and that was my central idea in the process development. Okay, next slide. Yes. What do I do? Okay. So I devised two vessels carrying out separate reaction. So here is reactor 1, here reactor 1 and here reactor 2. Two reactors are there. So reaction is carried out here. Excess and my primary aim should be to remove water. Water should be removed from it. So I am removing water by extractive distillation. This is a very familiar term for chemical engineers. So extractive distillation, selectively I am removing water, able to remove. So water, when I remove water, along with water some methanol comes out. Because only I can't do any chew. So along with moisture, methanol, so methanol acts like a carrier for the water. As soon as any water is produced, it takes away the water. Along with the water, some amount of methanol also comes out. So here Okay, just I'm sending it here to the second. So this plant is entirely for recovery of methanol. Here esterification takes place. Here excess alcohol, whatever I have used it, I am trying to recover it. So I have arranged this. These are the vessels which are used it in the process. The designs are all very well established. Okay, here is a packed bed column to enrich the methanol. Here is a condenser to condense the methanol vapors, and here is a drum to recover and refluxing. All these things are taking place. So here we add the feed. Here heating is required. When you attain the temperature of around 66 to 68 degrees centigrade, that is the boiling point of almost methanol. High temperature is going to be there. Reaction proceeds. When reaction proceeds, water produces. So what happens? Methanol, excess methanol is there. It immediately takes away all the water produced and comes out here. Here I am maintaining 99 almost boiling water. So flashing takes place because methanol boiling point is around 70 degrees centigrade. So immediately methanol vaporizes. It won't remain in the water. It vaporizes. Here is the packed bed distillation column. Enrichment takes place. Pure methanol comes over here. Condenser is there. So liquid. Here is the reflux for high purity. So pure 99, 98, 99% pure methanol is again sent back. So the process is run for some amount of time. That how much time I have done it several studies. In my report it is there. I will tell you. Next slide please. Yes, this is that is the idea, concept. Here is the real step. Here is the reactor, small, a 2-liter glass line reactor. Here is the feedstock, which I add fatty acid, then acid, fatty acid, then sulfuric acid, then some amount of methanol, whatever pre-initial required is there. Here heating is done by heating mantle, small quantities. Then so here you can just see here is the methanol plus water comes out here, and that is taken to a flash chamber here. Methanol produced vaporizes. This is a packed column, a reflux bed, and a condenser. So that condensed pure 99% methanol is again sent back to the reactor. Further reaction taking place. When all the reaction take place, what we do? I close this wall. So the next slide is there. Yes, this is a plant. This plant can produce up to 40 liters of biodiesel. Many people wondered. I took the sample to the NITK for engine studies. They were astonished. Sir, all people bring ml. You are bringing in cans. How is this? You tell me how much you want, I'll give you. Okay? So this is the 40 liters just in 2 hours. Produced. In my laboratory, I have produced it. Here is the flash chamber, distillation, packed bed, distillation. Okay? Then, yes, recovery here is there. Recovered alcohol comes over here and enters here. So the entire process runs, and these are the products which we have used. Sulfuric acid, then acid oil, then diesel, then biodiesel, crude biodiesel. All these things products are kept over here. Next slide. So at the bottom I get a mixture after the reaction, then do distillation, recovery of alcohol and all those things. Next slide. Yes. Composition of acid oil. I'm comparing acid oil, vegetable oil and diesel fuel. Just take into see. Acid oil, carbon. Vegetable oil, same. Diesel, much more carbon content is there. All analysis done by myself at various laboratories in Bangalore. I have done it, all comparative studies. Oh, this is you can just see here, hydrogen. Even hydrogen, diesel is there in hydrogen. Oxygen is not here. Oxygen is here because of fatty acid, COOH. Oxygen is going to be there. Nitrogen is going to be there. Coloring matter. So no oil, every oil has got its own color. It is indicating that what we say azo groups are there. Nitrogen derivatives, they are going to be there. Then C by H ratios, you can just see C by H ratio almost same, 6.6, 6.5, indicating acid oil is the best source for substitute for diesel. C by H are same. When C by H are going to be same, automatically properties are bound to remain same. They can't change much. Okay. Well, next slide. Next slide. Yes. Acid value, chemical properties. Acid oil, sunflower oil, all refined vegetable oils. I'm comparing it. Acid value is high, very high here, because free fatty acids, you can just see all are very low, because all is removed. So at that time only refined vegetable oils were required. So I'm comparing it. Saponification value almost same. You can just see saponification values are very near. Iodine values are very near. Only change is acid values. Next slide. Physical properties of acid oil, which I have done it. Acid oil, diesel fuel. Gravity. These are the flash point. You can just see there is a large difference between flash point around 60, diesel fuel around 200, because of the high molecular weights of the compounds. Okay. This is an energy content. You can just see energy content also is very this one close. Iodine value. Yeah, the diesel have no saponification in iodine value, because it is like petroleum fuel. No saponification, it is not there. All are compared here. Okay, next slide. Okay. When I produce biodiesel from acid oil, I got a property like this. Density. And this is standard, international standard. This is what produced by me, international standard. All are very close. And my biodiesel produce surpasses the international standards. You can test it anywhere in the world. Okay, next. Next slide. This is the diesel and standard diesel, which, because to test the fuel in the engine, I have to make blending and all those things. So I brought diesel from the local market, compared with standard biodiesel, whether any adulteration is going to be there or not. That also I have done it. These are given here. Okay, next slide. Yeah, spectra. The spectra are very essential to understand what is there in the fuel. Okay, you can just see here this group. This group is there in diesel. These groups are there in diesel, but only thing this group is totally missing. Next spectra, next slide is diesel only. There you find this is missing. Okay, just next slide. Just see. There is one more here, which is biodiesel, that is totally missing, indicating diesel fuel doesn't contain any ester group. Okay, next. NMR spectra. So each, what is A, what is B, what is C, what is D, everything is there in the self-explanatory, and you not again explain. This is this group, A, CH3 methyl group. Then this is K, ester CH2, D is here, D, repeat dominant. C, saturated group, unsaturated group, everything is self-explanatory. Each group is identified. Okay, next slide. NMR spectra, nuclear magnetic resonance, diesel fuel, aromatics are there. Next slide. NMR spectra of diesel, no aromatics. These compounds are there, ester compounds, large molecular weight, whereas diesel, no aromatic compounds are. Okay, next slide. Fragmentation. Flick to the compound and see what comes out. Engine, ultimately our main purpose is to see the performance of the fuel developed on the engine. So we are using a test rig. This is a test rig available in, at the time, during 2006 at NITK. Now much more advanced engines have come, but it is working. Okay, so this is the engine which I used it. This is the test fuel. Then all computerized graphics, everything, softwares were there loaded here. So here is the engine. Okay, next slide is specific. Here is a smoke meter. What are the smoke coming out from this one? Smoke meter. Next slide. AVL Germany smoke analyzer, what it contains, smoke meter and analysis of the smoke, whatever is there. Then next is sample studies. You can just see the thermal efficiency versus engine load. Very close. B100 means, to be very frank, I was the first man to demonstrate to the world 100% can be substituted. Earlier, all we were telling it should be not more than 20%. But no. In fact, the real performance starts biodiesel when it crosses 20%. Further studies I'll show you, biodiesel outclasses diesel. Outclasses at higher loads. At lower loads, no. At higher loads, it completely dominates the diesel. That is because of the compounds present in the diesel. It contains most of the aromatics. To break aromatics, more energy is required. So most of the energy produced by the fuel is utilized for breaking the fuel only. So less energy for the engine, less energy for the engine. Whereas here, all chain compounds are there. Chains you can break very easily. So more energy is available for the engine. So engine performs much more than diesel fuel. Okay, fine. So B0 is diesel, B100 is pure biodiesel. These are the blends what we have prepared. Okay, next slide. Fuel consumption. As you increase the load, brake fuel consumption decreases, specific fuel consumption. So you can just see B100, B0 is the top one. At higher loads, B100 requires less fuel. More load, less fuel. Okay, next. I'll explain. I can tell you why all those things they can. Engine torque, power. As you can just see here, B0 is this one here. Yes. At higher loads, surpassing. At lower loads, diesel performs better. At higher loads, biodiesel performs better. Lot of controversy for that statement. Okay. Then they did it. They did it studies. Then they came to me. Can you explain it? Why it happens? I explained the chemistry later on. Okay. Pressure. Feeling how pressure takes place. Pressure development takes place. This is at no load. Pressure, no engine load is not there. So automatically low pressure. You can just see here the pressure is, this is 0, this is 100, 10, 20, 30, 40, 50. This is about 10, 20, 30, 40, 40, 44. At no load, diesel performs better. As you increase the load, 100% load, full load, next slide. Let's see. This is around 100, 80, 90, 70. This is almost 55, 70%. Next, gas analysis, flue gas analysis. Pure diesel, 100% diesel, carbon monoxide variation, toxic variations. You can just see biodiesel produces less carbon monoxide at any load, much compared to diesel. Okay, next slide. NOx are higher. Biodiesel NOx are, because it burns very fast. Diesel burns slow. In fact, that is the reason why power produced is more. Fast burning, high temperature, energy released very fast, nitrogen reacts with oxygen in the air, it produces NOx. So NOx are higher compared to, in fact, that is one drawback. Okay, next slide. Smoke opacity. Soot compounds, carbon, biodiesel has almost nil, very low compared to diesel. So you can just see, very low diesel, this is diesel. So more amount of smoke is there in diesel fuel compared to, in fact, when I run the engine, it was like a cloud, white cloud. Almost no carbon coming out from the engine, free carbon. Next. So conclusions are, biodiesel produced from acid oil meets the international standard. Engine performance are comparable to diesel fuel. At any load, we can compare it. Toxic emissions are considerably reduced. Acid oil contains FFA, moisture beyond specified limits. Conventional trans-esterification cannot be employed. You cannot use conventional trans-esterification for biodiesel from acid oil. So you have to go for ED3R process using acid catalyst. Automatically you can produce biodiesel, and biodiesel produced meets the international standard. So you can trade across the world anywhere as you like it. Acid oil is commercially available. It is ideal source for engineering scale operations. Later on, these people at their instance, I developed myself with sir. We proposed one continuous process plant, that is in the next slide. Next slide, Toshi. This can produce 50 tons per day. Continuous process. Earlier was a batch process. Now it is a continuous process. We have shown how can be done it. So there are some deviations. Batch process, small scale. Engineering considerations are totally new plant. So this is how it can work. It has to work. It can work it. Yes, next slide. Thank you for your attention.